Today we study electromagnetic waves. Until now we have constructed four Maxwell's equations, and the most important point that Maxwell has discovered is that electromagnetic wave travels with the speed of light. So any electromagnetic field travels with the speed of light that is known at the time visible light. But in addition to the visible light, there are many electromagnetic waves. Near the visible light, there are infrared, mostly related to heat, and ultraviolet. Both infrared and ultraviolet are not seen with our bare eyes, but it does exist. Depending on the wavelength or frequency, they are classified in this band. We say this as Maxwell's rainbow. Before Maxwell, the rainbow was constructed with the visible light only. However, it extends very, very far away from the visible light. The infrared and ultraviolet are nearest neighbor of the rainbow, but outside with the shorter wavelengths, there are X-rays and gamma rays. This is a huge, wide spectrum of Maxwell's rainbow. If you go longer wavelength, we reach radio waves and long waves and so on. They are in units of meter in wavelength, units of hertz for the frequency. Maxwell showed that light is an electromagnetic wave. Based on the wave equation he formulated out of four physical laws, two Gauss Law in vacuum, two Gauss Law, and Faraday's law. And Maxwell's law. Here, this is mu0 epsilon 0. Oh, this is electric field. This related to displacement current. The radio wave was discovered by Hertz. The Maxwell's rainbow is the full spectrum of electromagnetic waves. And radio waves are widely divided into various spectrum. We use FM radio, that is of order 100 megahertz, AM, and TV channel. traveling electromagnetic waves. These four Maxwell's equations lead to a unique wave equation, and the same operator applies to the magnetic field. And these two relations shows that electric field and magnetic fields are orthogonal. We shall find that electric field, magnetic field, they propagate along a certain direction. This is the direction of propagation, and electric field, magnetic field, and direction of propagation is just like unit vector of x-axis, unit vector of y-axis, and unit vector of z-axis. So E vector, B vector, K vector is similar to unit vector of x-axis, unit vector of y-axis, and unit vector of z-axis. Atoms and nuclei can radiate electromagnetic waves following quantum physics. The nucleus consists of protons and neutrons, and outside electrons outside, and this is an atom. The electron make a transition between two possible quantum states. During the time, if it goes down to a lower energy state, a single photon is radiated, or if it is excited for lower state to the higher energy state, then it accepts the electromagnetic field as a photon from outside. In this kind of way, electromagnetic wave is radiated from atoms. It is similar to the system of LC circuit. There is an oscillating electromagnetic waves. The magnetic fields oscillates inside LC field, inside the inductor of LC circuit, and electric field changes depending on time. Changing electric field generates the magnetic field because of Maxwell's law. Changing magnetic field generates the electric field because of the Faraday's law. Distinct feature of electromagnetic wave. Electromagnetic waves travel through the vacuum as well as through medium, but water wave, sound travels through medium. For example, air, water, or solid. However, sound cannot travel in the space or vacuum. No sound at all. However, electromagnetic wave travels from the sun our Earth, electromagnetic waves travels along the space. There's nothing, vacuum. So this is the only wave that travels in through vacuum. Every electromagnetic wave travels with the speed of light in vacuum. This is another important point. 299,792,458 meter per second is uniquely defined for every non-exception, every electromagnetic field in vacuum. We return to the four Maxwell's equations. There are two Gauss law that depends on the divergence theorem. To derive the differential form. Stokes theorems Stokes theorem can be used to replace the integral form of the Faraday, Maxwell Ampere law, these forms. A charge at a point radiates electric field if its charge is positive. If we integrate over a closed surface surrounding the charge for the scalar product of electric field with the surface element, that is phi E, electric flux. That electric flux is proportional to the charge, and applying divergence theorem, the differential form of the Gauss law for the electric field is expressed in this form, and because this is the charge density, and in vacuum it reduced to divergence E equals 0. Vacuum. Case of magnetic field, there is no magnetic monopole. Field flux integrate over a closed surface is always vanishing. So whether it's a vacuum or not, divergence of magnetic field is 0. When we solve the differential equation, we usually use some trial solution. The wave nature of the trial solution, space-time dependence, can be simply expressed as exponential I kx minus omega t style. This is and omega over k is speed of light. So e to the I k x minus ct can be substituted to find out the space-time dependence of the solution. Sure, we multiply the sum vector, because electric field and magnetic field are vectors. So this is a scalar vector, that determines the wave nature of the electromagnetic field. If we apply the gradient to exponential function, for example, e to the ikx partial derivative with respect to x is just ik e to the ikx. In a similar manner, e to the ikx k dot x is e to the I k1x1 k2x2 plus k3x3. So if I apply the gradient to the exponential ik dot x, then what I obtain is e1 hat x1 partial derivative, e2 hat x2 partial derivative, and e3 hat x3 partial derivative. So if I substitute in here e to the ik vector dot x, same thing, what I get is common factor e to the ik dot x, and e1 vector is k1. Sure, I have additional vector of I, e2 hat k2, and e3 hat k3. This is just the ik vector e to the ik dot x. Hence, divergence of some vector e to the ik dot x, and this is actually ik dot vector e to the ik dot x. Because divergence E equals 0, and this is never 0, we say k dot v equals 0. That means electric field. This vector is some vector independent of space and time, but it is proportional to the electric field. That means electric field and the propagating wave vector is perpendicular to each other. In a similar manner, divergence B gives this one is 0. In summary, electric field is perpendicular to the direction of propagation, and magnetic field is perpendicular to the direction of propagation. They are perpendicular. Therefore, electromagnetic field oscillation is transverse. It is not longitudinal. Sound wave is not longitudinal. This wave is this is the direction of propagation. The magnetic field oscillates in this way, perpendicular to the direction of propagation. Another important point that we could derive from the remaining two Maxwell's equations is that, see this, again, curl E can be computed, curl vectors e to the ik dot x. This is a trial solution. If I apply the gradient operator, it becomes I k cross v e to the I k dot x. And magnetic field. So let me write this is let me write this vector instead of v. Write it as some e and b. Sorry, calligraphic letter. Still e. Magnetic field minus round t round magnetic field vector that is independent of time and space coordinate wave. Because it's a wave, we actually need to add additional piece minus omega. But then what I get is minus omega for the time derivative. So plus I v. This vector, the same. So what I obtain is from this relation I k cross E equals IV. Sure, omega is there. I cancels. K cross E equals omega over K. This is the speed of light. CV. So this really Faraday's law shows that K cos E equals CB. So in a similar manner, we make use of Maxwell's law in vacuum. Maxwell's law in vacuum. Maxwell's law in vacuum. Curve B IK cross B and this one is 1 over c squared. 1 over c squared time derivative of electric field. We have okay, so comparing these two, so I cancels, minus sign, so B, if we exchange the order, we can remove the negative sign. one C is multiplied in here, and we have okay. So in summary, this K vector cross E, where E is E vector e to the I K x dot minus omega t, B equals B K vector, K unit vector multiplied by K. So this one, from this one, we have K unit vector cross E vector this is the speed of light minus omega t gives positive sign C B, and from this relation K cross B minus omega t minus omega 1 over C squared E. So this again, we use this to find out this is K unit vector K cross B, and this one is multiplied, divided both sides, so omega over K 1 over C squared, or C over C squared is 1 over C, and C is multiplied to the left, K cross CB vector equals minus E. This one shows that electric field, magnetic field, these two are independent of space-time coordinate, and direction of propagation in this way, K vector. They are making a cyclic triad. So, from Maxwell's equations in free space, we have obtained a very, very important results. All of the electromagnetic fields are traveling with the speed of light, and with respect to the direction of propagation, electric field the speed of light multiplied by the magnetic field, their cross product is the direction of propagation. And the oscillation, the vector, electric field vector and magnetic field vector They are both perpendicular to each other and perpendicular to the direction of propagation. And the direction of E field, B field, and K field, the wave vector, they are just like X or Y, Z axis. They are perpendicular, E, B, E, C, B, K, or C, B, E, C, B, K, E, K, E, C, B. Okay. Try a solution for Maxwell's equation in free space. Actually, what we have done is this, and let us review what we have done. Just like what we have done with the RLC circuit, we employed the complex variable phasor analysis, called the phasor, for the solution for the electromagnetic field. The reason is that the coefficients of there are no coefficient, this is the coefficient, but this is 1 over c squared, that they are all real. Therefore, complex solution exponential I theta style applies. The phasor is particularly convenient because the derivative and integral are both exponential functions with an additive phase constant. The sinusoidal function can always be extracted by taking the real or imaginary part of the complex number. Alright, we consider the propagation of waves along the z-axis. Hence, the wave vector is wavelength divided by 2 pi. Really? No, it's opposite. This is wrong. 2 pi over lambda. This upside down. And angular frequency, 2 pi over period, or 2 pi nu, or 2 pi f frequency. So f nu, a frequency. Any wave propagating along the z-axis with the velocity c must be of the form as kz minus omega t. K is replaced with the 2 pi over lambda. Omega is replaced with 2 pi over period. 2 pi is factored out. It becomes, we can also factor out the wavelengths outside. Then what we have is wavelength over period. That is also, this is 1 over wave number, and this is omega. So this is omega over k. The z minus the ct. So any function of z minus ct could be a solution for the Maxwell's equation. And for convenience, we use exponential function. And to consider sinusoidal solution, it is good to extend to the complex form sum over amplitude multiplied by the exponential I something. Here, exponential I something is kx minus omega t. Hence, this is the vector parallel to E, but it is independent of X and T. The magnetic field is also written in the form this B vector is independent of X and T. If we substitute this one into the Faraday's law, gradient, it pulls out IK and unit vector along z direction, that is k hat, cross electric field, alright, and minus time derivative of magnetic field, minus plus I omega. I cancels and we find CB, this omega over K equals C. The CB vector is K cross E vector. We could have included the general phase of phi to allow the difference between the electric field and magnetic field phase. However, this identity, this relation, shows that phi equals 0. So E and B are in phase. Next, we consider Maxwell's law. Ampere's law is U0J, and in the vacuum, Ampere's law does not apply, and we consider displacement current. So that is the Maxwell's law. Substituting these trial solutions, what I get is IKK hat and this vector B, okay, mu 0 epsilon 0 equals 1 over c squared. And the time derivative of the electric field gives minus I omega. Canceling the common factors, what we obtain is electric field omega 0 here, k hat cos B equals minus u0 epsilon 0 of B no B E. Alright, multiply and we have omega here. Dividing omega both sides, k, there's k hat k over omega k hat cross B minus u0 epsilon 0 E, right? And this is 1 over C, and we multiply C to the magnetic field, then we have to divide C. Therefore, 1 over C squared K hat plus B equals minus U0 epsilon 0 E. Therefore, we multiply C squared here and flip the order as a CB equals. So this is a C. So we obtain this. As a result, electromagnetic field propagates along the K hat direction. So magnetic field with C multiplied and electric field, we have this triad. Let us review some vector calculus identities. Here, no x, no y. Therefore, the gradient is I x derivative, j y derivative, k z derivative. However, this function depends only on z and t. This one does not contribute, and only this term contribute. So k hat and z derivative. Chain rule can be used to find the overall vector k and unit vector k and derivative of this function. Therefore, gradient of exponential is ik, k hat, and exponential. Let us look into the previous relations for the amplitude. So electric field was expressed as E to the I k dot x minus omega t. B magnetic field e to the I k dot x minus omega t. And these amplitude satisfy the following equation. Because electric field and C times magnetic field, they are all perpendicular to the direction of propagation. It is, in general, there is a plane, xy plane, that is perpendicular to the z direction. In general, x-axis, y-axis. Any electric field, this is composed of Ex and Ey. So, electric field, we say this is polarization vector. Polarization vector is the vector, either electric or magnetic field vector, perpendicular to the direction of propagation, and that is independent of space and time. That is related to the amplitude of these electromagnetic fields. So, if Ex exists along the x-axis, then the corresponding magnetic field is By, CBY, along the y-axis, and direction of propagation is k. In such a manner, electromagnetic fields are correlated. Another point we had better to review is electromagnetic fields satisfy the wave equation. We had Faraday's law, and Maxwell's law in vacuum. Take the curve of the first equation. Derivative can be made in this way because the x derivative, time derivative, they commute. Then we can apply Maxwell's law on the right side. Then we have is double time derivative of electric field. And what about this? We remember back-cap rule. A cross B cross C back-cap rule. Just like the back-cap rule, curve electric field back cap, but the derivative operator must appear on the left side only. We know in the vacuum divergence always vanishes, so this curve is Laplacian electric field. This is called Laplacian. And Laplacian operator is this. Sum of second order derivatives of the space. If we replace this one with minus Laplacian, what we get is we can remove the negative sign both sides. What you obtain is electric field Laplacian subtracted by 1 over c squared. This is true. Times second order time derivative. So wave equation. Finally, electric field and magnetic field satisfy the wave equation, and actually this was U0 epsilon 0. Maxwell found that these numbers, product of these numerical values for the permeability constant and permittivity in the vacuum is approximately at the time, at the level of accuracy available at time. It was speed of light, 1 over speed of light squared. So electromagnetic field travels with the speed of light. Next, we consider energy transport and the Poynting vector. We have found the electric field and magnetic field, they are in phase and they are perpendicular to the direction of propagation, and directions are completely determined as this. And the unit vector is called the Polarization Vector, and the electric field and magnetic field polarization vector is K cross epsilon hat. And these are amplitudes. We have found that they are related in such a way that E, V, and K are ordered as X, Y, Z axis. In addition, speed of light multiplied by the magnetic field amplitude is identical to the electric field amplitude. We consider electrostatic field energy, just like the energy saved in a capacitor. So this amount of electrostatic energy is energy density multiplied by volume. So we compute the electrostatic field energy as an energy density, and the corresponding energy for the magnetic field can be computed in such a way. So we make use of this trial solution with condition to compute this amplitude square and space-time dependence amplitude square, that is a C to mu. This one can be CBM squared multiplied by C squared, and that C squared is 2 mu 0 epsilon 0 mu 0. So mu 0 cancels, and finally this is epsilon 0 CPM squared, and this is CBM. This is CBM is the same as EM squared. Therefore, they are identical. They are identical. And we want to compute the space-time average value of this. And sine squared theta has period of pi. This is 1/2. We computed it to compute the RMS value for the signal in alternating current is applied. As a result, electric field energy is 1/2 epsilon 0 EM squared This is 1/4. And this is 2. Because this space-time average is 1/2 EM squared. So 2 to 4. In a similar manner. So sum of these electromagnetic field energies 1/4, and sum of these, and we notice that this is 1 over mu 0 c epsilon 0 is a c squared, and this is cbm squared is em squared. And finally, epsilon 0 c squared equals epsilon 0 mu 0 epsilon 0. So epsilon 0 cancels, so this one does not appear. Okay. Energy flow. The explicit form of the amplitude is Em multiplied by some unit vector. This one can be explicitly written as xy component. And we know we have Ex. This one corresponds to the amplitude for the y component, and y components correspond to minus x component. So this magnitude is the same, and the sign stands for the orientation. When E is in this direction, B is the same magnitude but minus x direction. And direction of propagation is k. All right. So unit vector along the electric field and unit vector along the magnetic field, that can be computed exactly as a k vector, that is a unit vector along the axis of propagation. Next, we consider electric field cross product with the magnetic field divided by mu 0. If we compute this, and this stands for the average value, we know that B m equals Em over C. So Em squared, and Bm is Em over C, so Em times Em over C gives Em squared and C in the denominator. And this time average is 1/2. So we have 1/2 here. we have 1 over c mu in the denominator, and why don't we multiply c epsilon 0 mu 0. So we multiply epsilon 0 in the numerator, and this guy, this is 1 over c multiplied by c squared, that is c. As a result, the complete expression is unit vector k hat and speed of light multiplied by 1/2 epsilon 0 em squared. This is the rho. That means rho e plus rho b. This amount is. So rho times velocity, density times velocity. That is current density. If the density is for charge, then electric current density. If the density is for energy, then the energy current or energy flow density. That means this is the defined by Poynting vector, and Poynting vector stands for the energy density flow in space. That means if we integrate over some surface, then you will get intensity. So delta T, delta E per delta E. And because this current density is along the direction K with the amount of energy deposit per unit area per unit time. So Poynting vector is a very, very important object that stands for the energy transfer of electromagnetic field in vacuum. This vector 1/2 comes from the space-time average, and that vector 1/2 can be considered as this is m squared instead of RMS squared. All right. Radiation pressure. We shall find later when we study relativity in detail. So let me pass this part. Let us postpone studying this part after learning relativity. Radiation pressure is also like that. This we already have studied: propagation direction, electric field, magnetic field. This vector is transverse on the if it is along the z-axis on the xy plane. So polarization vector is a two-dimensional vector. When the direction of the E field is randomly distributed, we say it is unpolarized. If a single direction is projected out, and if we remove any direction perpendicular to that one, we say it is a polarized. Practical application can be found in this. Because we have concentrated on the electromagnetic field propagation based on the Maxwell's equation, we have not enough time to consider seriously about the refraction and reflection that we have already studied in high school. But let me briefly review that part in a very simple way. When light travels through two media, for example air and water, it reflects into the same media. It passes through the boundary interface, and when it passes the interface, the path is deflected, so that is called refraction. The direction of incident ray is defined in terms of the incident angle. That is the angle between the ray, incident ray, and the normal to the interface. In a similar manner, angle of refraction is defined by the angle between the refracted ray and the normal direction relative to the interface. In vacuum, speed of light is fixed, but this is called index of refraction. Speed of light slows down when the medium is present. And depending on the medium, the rate changes. For example, diamond, a very dense material, speed of light decreases a lot. In the air, it is very similar to the vacuum, but anyway, it is slower than the speed of light in the vacuum. When the medium is the same, N1 and N2 index of refractions are the same, then the light does not deflect. When the index of refraction is greater than the index of refraction of the incident, then angle decreases. Incident angle is greater than the refractive angle. In opposite case, the angle increases. So air to water and water to air, something like that. There's a chromatic dispersion. The index of refraction depends also on the wavelength. Depending on the wavelength, the index of refraction may also change. Because of this, let's see, index of refraction increases as the wavelength becomes smaller. Therefore, the light, blue light, that is a shorter wavelength, red light does not deflect a lot in comparison with blue. It wants to go more straight, and blue wants to scatter. The angle of refraction is much different from the angle of incidence. From glass to air is the opposite direction. Anyway, red light, longer wavelength tends to go more straight than the shorter wavelength. Because of this, we have chromatography. For example, if the white light passes through a prism, we have spectrum. This is IR and red, blue, and UV. The shorter wavelength, the more deflected. Another application in nature is rainbow. Spatial boundary condition can be considered to find out the rainbow appears with the angle of 42 opening angle. And I hope you can follow this to find out the primary rainbow with the angle of 42 degrees. This is called the primary rainbow. And you will also find the secondary rainbow. Perhaps you might have noticed that the primary rainbow and secondary rainbow, they are opposite in order. The explicit computation of primary rainbow angle is given in this page. When the light travels from a more dense material to sparser material, special event appears because of the deflection. If you increase the angle of incidence, at some point 100% of light travels parallel. And then if we increase the angle further, no light travels passing the interface. Only the reflection exists. That is called total internal reflection. That can be computed with this. Wait a second. Okay. And another important reflection is the Bruised Angle, theta b. Here, light has two polarization states. Incident unpolarized ray has direction of propagation. Polarization can be any direction on the xy plane when the light travels along the K. However, at some angle, which is called the Bruised angle, only the light, here we have two directions, either or this, but only this direction, this or that direction survives and perpendicular, this transverse direction cancels absolutely. That is called the Bruised Angle. And condition for the Bruised Angle can be computed in this way. Reflected light is perfectly polarized along the horizontal direction. Then refracted rays are partially polarized along the perpendicular direction with respect to the reflected light. The Snell's law stands for the relationship between the angle of reflection and refraction, and that can be applied to compute that angle. Okay, today the main theme was the traveling electromagnetic field and propagation direction, electric field, and magnetic field. They construct a triad, and Maxwell's equation reveals that the orthogonality of those relations. That's it for today.